Hello, everyone, and welcome to today's webinar, Smart Chart webinar series focused on TEM. My name is Rena Samsu, marketing at EAG Laboratories, a Eurofins company. Before we get started, I'd like to go over a few housekeeping items for today's event. All attendees have been muted. However, we'd still love to hear from you during today's presentation. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. I would now like to introduce Peng Zhang, Senior Director of Advanced Imaging Services.
Hello, everyone. Thanks for attending this webinar during this difficult time. So today we're going to go through TEM, and EAG is actually organizing a series of webinars, so keep tuned. Now, about myself, I'm a Senior Director of Advanced Imaging Services, and I have been in this TEM industry for over 15 years, mainly solving the industrial problems with TEM. So today's webinar, we're going through the following items. We're going to introduce you EAG, and then we have the smart chart, which is kind of like a roadmap for you to choose the right technique. Then go through the fundamental of TEM. It's just a couple slides, and then go through examples. So they are all real industry example, more or less like our commercial product that we can provide to our client. And then, like any other technique, there will be strengths and limitations. I'm going to talk about that. And then, of course, there will be other complementary techniques from our lab. So EAG is actually now a worldwide company. So we have TEM labs in 4 regions in California, specifically Bay Area, and on the East Coast, Raleigh, North Carolina, and Eindhoven, we have a TEM lab, and in Shanghai, we also have a brand new TEM lab. So we are everywhere. Also, we are, just to let you know, we are an essential business. We, for example, we support medical device industry, pharmaceutical industry. We also support semiconductor equipment companies, consumer electronics. So this is actually only a partial list of our industries. Okay, so this is actually a EAG bubble chart. So if you take a look at the position of EDS or I mean TEM, we actually cover the range somewhere at 1 angstrom level to maybe hundreds of micron in size. And then, of course, the concentration. So this size this axis is concentration. So basically, for chemical analysis, TEM technique typically is a if you want to know some dopant concentration, then of course a TEM is not the right technique for you. So we need a couple of atomic percentage in general. Of course, if you want to know dopant level type of information, we have other techniques for you. So the next slide. So today we're going to talk about really the industrial applications of TEM. So we have a group of scientists who contributed to this presentation, and as I mentioned, we have a lab in Kiefer, Sunnyvale, and in the Bay Area, and then Raleigh, Milpitas, we have another TEM lab. So first, I want to introduce you, the very famous Moore's law, and everybody in the semiconductor industry knows about this law. basically since 1960s, the semiconductor device is shrinking, continuous shrinking for many years already. And then this actually means the device is going to be smaller and smaller and smaller. And especially, for example, for this technology, in 2003, the industry actually, Intel first introduced the silicon germanium material, and then about 2006, 2007, you got the high-K metal gate technology, and later on, the device is getting more complicated, and then you get the 3D FinFET type of device. And then for the future, of course, you get the so-called gate-all-around technology. Is basically very complicated device structure. And then if you talk about the information age, you need to talk, discuss storage. Nowadays, if at home, you probably still own one of the hard disk drive. If you take a look at the hard disk drive in 1956, so this is really hard disk. I think it's about 18-inch in size. If you go to the computer museum in the in the Bay Area, you can still see one of the hard disk drive in the museum. And now, if you take a look at the history, the magnetic storage, density increased by order of 9. So this is a huge, very aggressive shrinkage of storage size. So for example, if you open up a hard disk drive, you will see a lot of elements involved. So basically, for the technology development, people always ask for high spatial resolution and high sensitivity, and we got all kinds of requests like that all the time. So for this talk, we are going to focus on transmission electron microscopy. But a lot of the real-world engineering problems, they need a broad spectrum of techniques, and a lot of these techniques are available at EAG. And also, this talk, we only cover a very small fraction of TEM applications, right? So if you have specific questions that you want to know more, then feel free to contact us. We'll have the email contact address at the end of this talk. And also, the examples covered only a very, very small fraction of the materials that we analyze. So again, discuss with us about your need. TEM. Actually, for this for this presentation, we focus a lot on the scanning TEM. I'm going to show you the reason. So this is a very basic introduction slide about TEM. In a lot of ways, the TEM is like the old projector, and the only difference is that the optical lens is replaced by electromagnetic lenses, and the light bulb is replaced by electron gun. And this is a real picture of a TEM. From floor to top is about 2.5 meters. And then in a TEM machine, it can operate two modes. One is called conventional TEM mode. So the thin TEM lamella is here, and your electron beam is parallel in this case. And then, of course, if you want to do chemical analysis at a very small region, then you need to do scanning TEM mode. In this case, the electron probe is focused onto your TEM sample, and then it's going to scan across your TEM lamella or TEM sample, and then do the analysis. I should say that for a typical TEM thin lamella, this sample thickness is typically 100 nanometer or thinner. But for some special case, that I will show you one example. For failure analysis, we actually use up to 1.5 micron, or even sometimes 2 micron thick TEM sample. to basically to include a large portion of your sample, but it's not very common. All right. So TEM, is indeed. If we go back to this slide, so this thin slice is actually is a feature, has certain thickness. So basically, what I will say, TEM, a lot of sense is actually a two-dimensional projection of a three-dimensional object, right? So for example, for this case is this company produced the Age of Apes, right? So this is a pretty good logo I can show you. If you take a look at the same object from different orientation, you will see different projection, right? The same type of effect actually exists in TEM. Right. So when your electron probe interacts with your sample, then it will generate a lot of secondary signal. For example, secondary electron, and you will generate X-ray. And of course, because your part of it or most of the electrons are transmitted, so you use it to form images. And there's also a technique called electron energy loss spectroscopy. Basically, a portion of the electron will lose energy, and then you can analyze the energy loss. So in a TEM, there are two typical contrast mechanisms. One is called a mass thickness contrast, and another one is diffraction contrast. So mass thickness is simple. This is like a ball. At the center of the ball, of course, is thicker, and then the feature will appear to be darker. And as for diffraction contrast, so for example, this is a pure aluminum alloy, and this lines, they are not foreign material. This is just because of the local defects in the matrix. So it will scatter the electron differently from the matrix. So it will give different contrast. So in a conventional TEM, on this side is called CTEM. Basically the contrast is a convolvement of mass thickness and the diffraction contrast. So this makes the contrast really complicated in some cases. And then, for example, in this case, if people really wants to only to visualize the defect, you can just switch to so-called bright field stem mode to basically visualize the defect without this bending contour. For a real sample, for example, this is a magnetic reader. You will see on the right side is a conventional TEM image, and you will see a lot of this kind of a diffraction contrast in your material. And then if you switch to dark field stem mode, you will see very nice dark and bright contrast, which is easy to understand. Now, if you go to atomic scale, and there's one thing very interesting is that in this quantum world type of structure, just based on the image contrast, you already see there are so many different types of materials involved, right? So you can immediately see that that there are heavy elements involved in these quantum worlds. So basically that is good advantage of a so-called Z contrast image. And the good thing about a STEM mode is that if somebody want to say they say I still want to understand the diffraction contrast in my sample, so you can collect a so-called bright field and dark field STEM image at the exact same time. So you don't need to choose one or the other. And of course, if you want to do a small area analysis, of course you can collect. Nowadays, you can collect the EO signal and the X-ray signal, and also the image at the same time. You don't need to choose which one to sacrifice. So I'm going to so basically whenever you want to see do the elemental mapping, basically your electron beam is rastering over the sample, and then basically it will collect a three-dimensional data set. On the x and y direction is the spatial information, and on the z-axis is the energy domain. And then based on this three-dimensional data set, you're going to basically reconstruct the elemental maps, right? So in this case, you basically integrate different peaks. So next slide. From the TEM nowadays, so this is a very famous paper by Professor David Muller almost 10 years ago, or actually more than 10 years ago, so that atomic resolution chemical analysis is available, right, on the commercial equipment these days. But I need to emphasize again and again, this sample can do such analysis doesn't mean that your specific sample can do that. It's because for such high resolution, you are pumping really a lot of electrons on your sample, and that will actually damage your sample most of the cases. And again, so this atomic resolution EDS is available. This is my data many years ago already. Okay, now application. What can we do about this fancy tool? Before we talk about the application, the first step of TEM will always about the sample preparation. So for a lot of challenging samples, sometimes the TEM sample preparation, or if we are not able to prepare the sample, then we cannot do the analysis. So nowadays, for industrial samples, solid state samples, maybe 95% of our samples are prepared by focused ion beam. Basically, you lift out the TM lamella, and then visualize from the cross section, and then you can choose where you want to lift out your sample, right? So I just want to have a separate, just brief introduction about this idea. Is that for TEM sample preparation, you basically slice away a material, and then you can visualize from the cross section. So if you do slice and a view, slice and a view, slice and a view, if you do lift out a block or mill away a block, then you can reconstruct a FIB-SEM tomogram to do a three-dimensional image. So this is actually a very nice technique that can bridge nanometer and micrometer type of problem, right? So you can sample micrometer cubic material. So okay, let's start with a very simple application of TEM. For example, dimension measurement. So this client wants us to measure the thickness between the on the sidewall of a semiconductor structure. And you can of course do the manual measurement. For example, if we measure this place, and just do the manual, but it's going to be very tedious, and it's not going to be very consistent. So we in our lab we use this algorithm. It's machine learning algorithm that you can measure automatically all these hundreds of measurements, automatic measurements, and then from the graph you can already see that the top is relatively thick, and on the histogram is on the right side or thicker side of the histogram, right? So you have a visual, and also you have quantitative impression of your device. So okay, now going to high resolution for optical material. In this case is a gallium arsenide related material. You can do the so-called bright field and a dark field at the exact same time, and you get atomic resolution. One of the, of course, the interesting the next step will be what is in this quantum well structure, right? So we can map out the individual element, and then the next step would be we can extract the semi-quantitative composition of the of the elements. In this case, we only plotted the group 3, aluminum, gallium, and indium. So you can see the nice fluctuation of element distribution. And another interesting question, of course, for thin film growth people, they really worry about how sharp is the interface. How quickly they can transit from one layer to the other. So again, because this image is mostly Z contrast, so we can plot the intensity of the stem image and then do the fitting, and then you can see that there's really some sharpness difference at the different interfaces. Now, another question, another property, I should say, very interesting would be what is the strain in this indium gallium indium gallium arsenide material. For that purpose, also indium gallium nitride. So because of the piezo effect, and then because of the strain, and then the illumination, the light emitting will be different, right? So people want to characterize the strain, and then we can do that, and then you can so again get the so-called GPA component. GPA stands for geometric phasor analysis, right? So and then there's a little bit of a conversion of the GPA component. So you just based on this analysis, we can conclude that the in-plane strain is about 1.2% compressive in the quantum well. So actually, for this particular sample, the GPA component and the EDS concentration actually agrees very well with the photoluminescence data. As I get feedback from my collaborator. And then with the GPA analysis, you can also, of course, study the interface between, in this case, is a sapphire and aluminum nitride. You can visualize the dislocation. I don't want to go through to the details. Now, the second one is a VCSEL failure analysis, right? So if you want to know more about VCSEL, there's plenty of Wikipedia introduction, but it is widely used in the industry these days. Facial recognition, 3D printing, and even your optical mouse. There's plenty of application. Right. In this case, is a CERN, is a big gigantic accelerator in Europe, and so they have a VCSEL failure analysis request. For us, we basically say, well, because we really don't know where this failure is, so we actually prepared, in this case, is about 1.5 micron meter thick plan view TEM sample, and then we see high concentration of dislocation networks in this device. Basically, this dislocations kill device. And then, of course, you want to know, because this is a two-dimensional projection of a 1.5 micron thick TM sample, the next question would be, how thick or which thickness or which depth is my dislocation, and then we can convert the plan view into a cross section, and then you will see that the defects is actually originated from the multiple quantum well light emitting quantum well region. So because of the high density of energy in that region, and then defects will originate at these layers. And actually, for a lot of the failure analysis, we start with a fault isolation technique. For example, electroluminescence. To find the hotspot of the failure site. and then with this, we basically label the field side, and then we cut through the region, and then we find a defect. So a lot of times for real engineering device, we do photo isolation as a first step. Right. And then, of course, for VCSEL, this multi-layer quantum well or superlight structure, you really want to know, the composition of the aluminum gallium arsenide, and also you are interested in the dopant concentration. As I said, TEM is not a dopant technology, so you want to use SIMS, and in this case, is a very nice example by so-called point-by-point picosims. We'll have some SIMS webinar following up if you are interested. Just keep tuned. Right. Another interesting application of TEM would be dislocation imaging and typing. For gallium nitride dislocation imaging, there is well documented in the literature. So you can do the so-called G.B analysis to visualize the dislocation, and then based on how they show up and how they disappear, you can analyze each individual dislocations, right? And nowadays, if you do in the past, the TEM is conventional TEM is widely used, but sometimes the contrast of TEM is pretty complicated. For example, this kind of a bending contour. But if you switch to scanning mode on the exact same sample, basically the image is kind of like flat, right? So make it more eye friendly, if you want to say that. So for most of the industrial problem, scanning TEM is probably enough to basically have a general impression about the sample. So now, if for some of the client, they really want to know what is the type of my dislocation, and then we have a technique called large angle seabed that we can, this is a diffraction technique. If you don't understand, ask us. I don't blame you. Basically, we use this diffraction technique to solve exactly the Burgers vector of your single dislocation. In this case, the Burgers vector is equal to 211 bar, 1 bar 3. So you can know this is basically A direction, and this is C direction, and now you know that the Burgers vector is actually A plus C mixed dislocation. So it's a very precise measurement. And okay, another one is that for TEM, one of the limit of TEM is that the sampling is really a problem, right? So if you really want to have a statistically meaningful analysis of your dislocation, we have a technique called electron channeling contrast imaging. Is the SEM based. So basically, in this case, we have the gallium nitride surface, and then you analyze the defect density is about 1E8. So if you want to know more, just let us know. So it's not the focus of this presentation. Okay, so now high-K metal gate reverse engineer. So basically, we buy this device from the market, tear it down. So one of the larger scale application would be using so-called PED, is precision electron diffraction. We can map out the copper line, and we also can map out the the tungsten metal gate in this case. So basically, you can map out the orientation, and also you have the grain size distribution of all these particles by electron diffraction analysis. And then, of course, again, dark field and bright field imaging, they complement each other in this case. And then if you zoom into the gate area, you already see the atomic structure of this metal gate, right? And then we can map out all these relevant elements, and then we overlay on the same graph. And apparently I didn't overlay silicon here because otherwise the layer will be very busy. And you can also overlay carbon, nitrogen, and oxygen is also analyzed, but is not included here for clarity. And one thing, so in the past, people just use EDS analysis, and this is actually a direct comparison of EDS and the EOS analysis. So in general, EDS mapping will be a little bit more noisier in this case than EOS analysis. So so for silicon devices nowadays, we can solve maybe 95% of the problems with EOS, slightly better than EDS. But EDS, will be a little bit quicker and dirty, do quicker and dirtier analysis. So just in case. So this is, for example, after we do the mapping, then you can do the semi-quantitative analysis across the gate. You analyze the nitrogen, oxygen, all the way to heavy element like tantalum, right? So of course you can do the same thing with EDS, but one of the problem of EDS in this case, for example, if you take a look at here in this region, you will see large background of nitrogen because nitrogen and titanium, they have very close peaks, X-ray peaks. All right, so if you do EOS, this nitrogen is not there, right? But if you do EDS, the EDS will not have enough energy resolution to separate nitrogen and the titanium in this case. So in case whenever you want to analyze a material with high Z and the low Z material, probably you want to consider EOS first. And another advantage of EOS, of course, is it has bonding information. And so this is a titanium, but it really depends on the local bonding. You will have energy shift of this titanium peaks, and you also the shape will be slightly different. So this has bonding information. So nowadays you can analyze semiconductor devices to very tiny structure. In this case, a 22 nanometer. You can do very nice EOS analysis from all the way from carbon, nitrogen, oxygen to tungsten, right? And with the state of the art focused ion beam technology, and of course a lot of experience, you can cut. So this device, for this particular device, the source and drain and the gate only separated by tens of nanometers. So you can have very precision, high precision sample preparation from these semiconductor devices. Now, for a lot of the the question is also related to interface. In this case, is aluminum nitride on 4H silicon carbide substrate, right? So if I'm not sure if you can see it, but there's a bright layer at the interface of aluminum nitride and silicon carbide. There's about 5-layer atomic layer of interface. If you do the A, B, C, this kind of configuration study, and then look into the literature, so this interface is most likely silicon nitride bonding over here, right? So basically, you can do interfacial study these days with a TEM analysis. All right, so of course you can also study the crystal structure within the so-called body of your film. In this case, is a complicated infrared light detector, and because of the Z contrast, again, is mass contrast scanning TEM. For example, in this case, you see that in the indium arsenide, one side of the column is actually a little bit brighter than other side. So basically it means we can decide the polarity of the group 3 of the compound semiconductor. Group 3 on the right side or left side. So you got this very important information. And a recent good progress of the scanning TEM technique is so-called ABF. technique. So you can visualize not only the high Z material, like in this case, you got the gallium, but in the so-called Z contrast, your nitrogen is missing. The reason is very simple. If you go outside right now, the sun is so bright, and then all the faint star will not show up in the sky, although they are still there, right? So you need some kind of filter. In this case, you use a ABF as a filter, so you can image both gallium and the nitrogen columns, right? So okay, another interesting one is about particle analysis. So when I was preparing the slides, I want to motivate my son. He's 7-year-old, and well, so this is science. And then you can basically map out the particle. In this case, marbles, and then you can basically measure the size. You get a nice distribution, and then you based on the color code, you immediately know that a number particle number 32 is the largest, right? So it's about 145 pixels in diameter. Now, so this is a SEM example, but on TEM images, we can do exactly the same type of analysis. So in this case, we basically automatically measure, right? So we automatically measure these particles. We have a very nice type of Gaussian distribution, and again, if you really want to know what is exactly the diameter of this particular particle, you can just go to the color code here or here. Is that is about 55 or 60 nanometer in diameter or pixels, right? So I'm going a little bit fast today. Just to want to know if there are many more questions. But I'm going to just summarize my talk here. So as you can see, that the transmission electron microscope nowadays is much more than a fancy camera, right? So you can do imaging, but imaging is really only the first type of application of TEM. It's actually a very powerful nano characterization platform. You can do a lot of things. For example, you can do in situ, you can do tomography, a lot of stuff. Again, if you have specific needs, just talk with us. And I want to emphasize again, the high resolution analysis and high sensitivity that is always expected, but not always possible. And these days, the resolution most of the time is limited not by the microscope itself, is actually rather limited by your sample, right? So that's the unfortunately, we cannot do anything about it at this moment. Also, TEM there are so many different type of techniques, so it's going to be very important to match your problem with the right technique. So I don't want to say match my technique with your problem. I want to match my technique with your problem, to basically to solve your problem. So whenever you have when I have a new request, I will always say, what is your problem? And then we'll design a TEM type of application for your special or specific material. And okay, so in real life, the real life project often needs a very fast turnaround time. So all the examples I show you in this presentation, they are real life example. And at EAG, we can basically give you the data with about 5 business days, and often we can do a little bit faster. So we have very quick turnaround time for real-time projects. To summarize, we can do it. However, TEM is not really a silver bullet. So there's a lot of limitation I want to really emphasize. The major limit number 0, right? So TEM is a damaging technique. So once the TEM sample is gone, and so if I extrapolate extract a thin lamella from your device, of course, the device is not really functional anymore. So you want to do TEM really as a last analysis for your problem. So always try TEM as the last technique if you really plan to do any other technique analysis. And limitation number one, I mentioned at the very beginning, TEM is really a two-dimensional projection of a three-dimensional object. So there's certain technique called tomography to solve the problem. It's actually a Nobel Prize winning technique. You can do that. So again, is basically as simple as that. You view the same object from different orientation, then you will have different impression of your object. In TEM, so this is our data, and you can. So in this case, is we can do a 50 nanometer diameter needle, and then basically you can do three-dimensional TEM analysis, right? So this technique is there. A lot of publication in this field. However, for the real industrial application, that there are still some limitation mostly limited by a sample. So again, talk with us if you really need this type of application. And limitation number two, I emphasize again that TEM itself is a damaging type of analysis. It involves ions for sample preparation, and it also when we do the TEM analysis, because of the electron has charge, so it can ionize your material, and also because it is a particle, you can also sputter away your material. So we need to be very careful, right? So again, back to our smart chart, and we are updating this plot from all the time. So again, TEM, the domain of TEM is from the size of kind of angstrom or sub-angstrom these days, all the way to a couple hundred micron. That's the maximum. So maybe 100 micron is probably the limit these days for TEM analysis. The concentration wise, typically is a couple of percentage, right? So for special cases, it can do a little bit better, but typically is I would say 1 atomic percent is the limit, right? So if you want to do part per billion, and then you can do for example, the SIMS analysis. And then we also have a powerful technique called atom probe. So that is kind of like part per million type of concentration analysis, and spatial resolution is sub-nanometer. Again, so atom probe is very powerful, is available at the EAG network, but it has a lot of limitation, again, set by your sample. So if you have certain application, just let us know about it. Why you want to choose EAG is basically, I think I want to summarize 3 words: we know how. So we have a lot of the state-of-the-art equipment. We also have a very experienced analysts in the field. And also, again, we are a type of essential business. During this difficult time, our laboratory is still open to support very essential industries these days, like pharmaceutical and the defense, for example.